Hello, Mark Biasetti, and back with another SolidWorks Tips and Tricks webcast. This February, I'll be presenting at 3D Experience World 2024, and one of the presentations that I will be giving is a technique for creating advanced consumer models. I've come across a technique in the last few years that's worked successfully for me in this area. Now, I know this area of creating advanced shapes is difficult and time-consuming and presents a lot of problems, especially when editing models after you've created them. So I want to present to you a technique that I've come upon in doing this the last few years that's really helped me to create robust models and giving me the ability to edit them quickly after they've been created. So let's just get right into it and let me show you this.
Welcome and thank you for taking time to attend this presentation. If you're like me, and probably why you're here is that you work in an industry where you create advanced shapes, namely the consumer product industry or medical industry or even commercial industry where you have ergonomic shapes that need to be created in SolidWorks. And the objective of this presentation is to share with you a technique that I've developed in the last few years to create these shapes, but create them so that they're robust. And that is, once they're created, you can easily modify them without them blowing up in shapes. So the contents of this presentation to convey a lot of information. I'll basically give you the objectives that we're after with this, a short introduction of who I am, stating the problem, what are the challenges, what's the solution, do some hands-on both between PowerPoint and live SolidWorks, and then give you a summary. So let's get into it. So the objective of this presentation is to share with you a process that I've developed over the last couple of years that works rather successfully for me when creating these advanced shapes. Not only for creating high quality shapes, but also having them be robust and editable, even though there's many features in them. So who am I? I'm Mark, and I've been in the product design world for more than 40 years now. Slide kind of dates me because my first job was Atari, and some of you don't even know what that company is, but a famous gaming company. I worked for them to create consumer products, basically the gaming controllers and gaming consoles. Went to HP for a while and then got over to IDEO and spent about 16 years with IDEO. And then in 2004, I left the product design world to go to work for SolidWorks as a product manager and then later product definition specialist, and had a lot of fun creating a lot of new features for all of you that had to do with product design. In 2014 I left SolidWorks to go back into the product design industry and work for Spanner, a small mechanical and product design firm here in my hometown of San Jose. And then just after COVID I jumped from Spanner over to Sarcos because of my passion for robotics and animatronics, and worked for them for a few years. Just had a lot of fun doing some really interesting robots. If you're not familiar with them, you might want to check out their website and check out their full-powered, full-body exoskeleton, of which I worked on for a while. Through these companies, I've had the pleasure to work for some of the Fortune 500 companies to help them develop their products. Had a lot of fun with a lot of these companies. It's been a great ride so far. So enough about me. Let's get on with this presentation and what the problem is. So if you're here in this audience today, you probably are one of those who create advanced shapes. And when you do create them, you know that they're a lot of work. They're not only a lot of work, but they're a lot of work to maintain. You can create a beautiful shape, but if you then go start to edit it or try to make it an editable parametric model, you'll find that it breaks rather easily. I know for many years in my career it has and still does do this, so it's kind of a pain. It takes a lot of experimentation along with that to arrive at the right shape. It takes a lot of features, and you have to pay a lot of attention to aesthetics, which I won't get into too much in this presentation. I have other presentations that talk about surface modeling, and I'll give you a referral to those later in the presentation. When I talk about models being fragile, you know what I mean when I say tree of blood. You know, that's our catchphrase in the industry when things go bad in the feature manager. And it takes a lot of work to repair models, especially with lots of features and a lot of surface features. They can also, because of the number of features, they can be confusing to edit. It's hard to know what caused what and to roll back and find the source of the problem. And then more importantly, after you create this beautiful shape and it goes into some of the later stages of the concurrent engineering process, changes occur, like maybe the batteries get bigger or something and you have to change the overall shape. Well, then you have to deal with all that tree of blood all over again when you start to make changes. So really what this presentation is about is to share with you a process to overcome some of these limitations and to be able to create not only an aesthetically beautiful ergonomic model, but also make it robust when you do have to do changes. And I have a technique to share with you that is semi-successful that I've been using now in the past few years. But it kind of goes without saying that there's different levels of modeling in SolidWorks. I mean, if you are basically the extrude, revolve, fillet, chamfer type of person doing machine modeling, SolidWorks is beautiful. You can modify anything and update anything. Everything works. You go home early. It's great. If you're into surface modeling, you can know how frustrating that can be. It's a whole different ball game. And it's either something that you love or you hate. I'm on the love side because I love the challenge and I love working on this kind of modeling in the injection molding industry that I'm in. But I have lots of colleagues that are on the other side that hate it, and they stay away from it like a plague because they know how much of a pain it can be and how much time it can take. What really identifies the problem is that for surface modeling, it requires many features. And once you have many features that are dependent on one another in the tree, you're increasing sometimes exponentially the amount of potential failure because so many things are built on so many things. It's like a house of cards. You have a lot of dependency on one another, so the chances of failure are increased. As in this example of this model, where just one change by half an inch of that feature turns the feature manager into that tree of blood. And so this is really at the crux of the problem. And this is what we have to deal with as advanced shape designers. So what causes this problem? I mean, why isn't SolidWorks robust no matter what you do in it, whether it's simple modeling or advanced modeling? Well, part of it, and I have to put this up front, is poor design intent on the part of the designer. So SolidWorks is not AI yet, and it doesn't understand what we want. We have to tell it what it wants, and we have to be explicit about that. Part of the problem is SolidWorks' fault. The constraint solver has bugs, especially the 3D sketch solver, which from my understanding working at SolidWorks is a different solver than the D-cube solver they use, or whatever solver they use for 2D sketch is different from the 3D sketch solver. Also, if you think about it, and I know Ed Eaton goes into this in a lot more detail, that surface bodies are not as explicit as solid bodies. If you think about a solid cube, it is 6 sides and it's a closed manifold shape. That's can be represented also by 6 surfaces, surface bodies that are connected. But unlike a solid body, it's not manifold. It also, each of those surfaces has its own edge. It has 4 edges, and it also has 2 sides of the surface. It also has vertices at its corners. So when you're talking about surface modeling, you have a lot more internal IDs to track. You have a lot more variability or things that need to be solved. And that's why solid modeling and SolidWorks work so well, because they're manifold closed shapes and they're well understood, and there's less variables than there are in surface modeling. Another part of the problem is that in creating advanced shapes, we by nature also create the underlying curves that create those shapes. And those curves oftentimes are defined by splines, both 2D and 3D. Now, splines in SolidWorks are parametric splines. They're not like Rhino or like Alias, where they're as parametricized as they are in SolidWorks. And because they are, they can easily over-constrain. They can knot, and they can get to beyond their solvable parameters. And that's why you see sketch splines do this, especially if you move a point in 3D space and its magnitude of that end of the spline knots over or crosses over itself, and it fails. So sketch splines are a special breed that you have to take care with, and I can give you a few tips on how to do that. SolidWorks isn't a perfect modeler, and there's still things to solve, and they still have work to do. And hopefully we'll get to that point where you can do anything and have anything solve. But for now and today, it's not that way. So another part of the problem that's, if not obvious to you now, is that when you have SolidWorks parts with many features, you're increasing the chances of failure, because all those features, many of those features are dependent on one another. So you're just increasing the chances of something not associating with, I'm sorry, a child feature not associating with a parent feature, whatever that constraint is. Again, I talked about the curves. They can easily knot and over-constrain. And then I also alluded to the fact that surface modeling has many more IDs, or internal references, to track. As you, especially if you split a body or it's a surface that's split or trimmed, there's a lot more to consider to parametrically associate with. From the designer's end, you also need to take special attention of what you're referencing when you build your models. And what I mean by that is when you are building a feature midway or late in the tree, and you're referencing a fillet edge or a surface edge, it's really a better practice to find the original source of that surface edge, that is the curve or sketch, and reference it instead of the surface. Because by that you're stepping through less successive references and going back to the origin, and that just makes for a better practice. And then another point that I'll expound on too is that a lot of times we just jump in and we don't really plan out our approach, and this is really important. As we build up experience in building these kind of models, we learn from our past failures, and by learning from our past failures, we can plan for the future. But taking the time to plan ahead and learn and kind of strategize and visualize how you're going to build that model is really an important step. So what am I offering in this presentation as a solution to all of this problem with building advanced shapes? Well, I want to share with you a technique that I developed over the last couple of years that really helps me to build advanced shapes and build them to be aesthetically and ergonomically beautiful but also to be very robust and editable, which are, as we've already talked about, can be a contradiction, as we all know, as we build these advanced shapes. So basically, this slide lays out the steps that I take, and I won't go through all of it here, but I'll illustrate it further on in the presentation. But basically, it's this. So you start with a conceptual phase, and in this conceptual phase, you're experimenting. And I found even now, like 20, 30 years into SolidWorks, or 20 years into SolidWorks and other modelers, that I'm still experimenting. Even with shapes that I think I can do, I find out I can't do them, and I have to take another approach. So experimentation and having a conceptual phase where you just kind of freewheel it and you just experiment is really important, because you don't want to be doing that like, midway through your design process. You want to get that out of the way up front and really understand the solution before you take the steps and invest a lot more time into your model to refine it. So once you get that conceptual model for your shape and you feel good about it, you think it's a good approach, what I'm recommending is then I want you to trash all your surfaces. Yes, that's right. I want you to throw away all of your surfaces and keep your curves. Now, with that, you have a curve model, but you have a lot of dangling curves. But before you do any of that, I want you to save a copy of your conceptual model and a copy of your curves. I'll talk more about that. And then the really important step and kind of the game changer here is I want you to rebuild your curves as a curve network, meaning that I want you, instead of creating curves on surfaces, creating another curve on another surface, and so on, I would want you to create as complete as possible a network of curves that defines your design intent of your model. And do this so that you have a complete curve network, or almost complete, and then you build all of your surfaces successively on that. And then once you have that, you want to test and refine your model to make it more robust. You're going to find that your first attempt is pretty good, but it's not completely bulletproof. So there's a phase here to test and refine. So we'll get into this in a little more detail, and let's talk about these steps. So the first step is you want to have some good references, and you want to have a good ID sketch. Most of the time they're 2D sketches in Illustrator or Sketchbook Pro, and you might have some 2D, you might have some 3D. You want to lay out this in as the first features in your model, and have them as a reference and follow them as closely as you can. And with that, you might have something like this. So let me roll back into this first conceptual model to the very beginning and turn on these two sketch pictures, and we have some imported bitmap images of the controller, both the front of it, the side of it. We can put in more views, but usually it's two views like this that work. And the idea is to use these as reference to follow, not explicitly, because a lot of things when you draw in 2D you can't predict in 3D, so there's going to be changes that'll be made. But for the most part, you're kind of showing the side profile faithfully as you build up the model and its top view. So with that, let's go back to the presentation and talk a little bit more about strategy. So once you have those references, then you kind of understand the shape from a two-dimensional aspect. You want to think in 3D. Now we know that models like this cannot be built in one feature. That is, unless you're using something like 3D Sculptor, and that was really the impetus back in 2010 to create that product, is to eliminate all of these features and build everything out of one sub-D shape. And it does work rather well for that, but there's some downsides to that also that I talk about in one of my webinars if you want to go to one of those. So planning out the strategy, visualizing how do you break this down into its various subsurfaces to complete the entire shape. And so that's really valuable to be able to visualize that before you even touch CAD. But once you do understand what you think might work, then you can start with your reference, and with that strategy, you can start to build up your model. So it's really, I know this image doesn't really show it, but I often like to approach the tough problems first and leave the easy stuff to the last. So really the toughest part of this controller is the transition from the elliptical shape up front to the handle. But I do want to establish, as I conceptualize, I don't worry about that. So in my conceptualization, I build some of the surfaces I know how to build. So the dome, the fill dome on top, the section of the handle, these are easy to do. And so I establish those along with the curves that define them, and then I work on the tough areas. And then once I have a model that I think I know how to build it into a successful shape, I look at it and I evaluate it. Now, it doesn't have to be perfect because it is a conceptual model. And if I show this model again in SolidWorks, and this is the conceptual stage of the model, let me just hide those sketch pictures. You can see the network of curves that I built up. You can see the shape. If I hide the curves, we have something that looks pretty good. I'm pretty happy. I think this is going to work. It's not perfect, but I have the opportunity to get it more perfect as I go to some of my next phases of this process. So with that, this is kind of the controversial part of this process. Is what I want you to do first is make a reference copy of all those surfaces. And the way that you would do that normally is to go into the model and collect up all of your surface bodies, and then go ahead and do a save as either a step or a parasolid model, and just save that off to a local directory. And then we're going to re-import that into our new, more final model solution. As well, what I want you to do is to be able to copy all the curves of the model and save them as a 3D sketch. I'll show that in another model. So we want to save off our copy as a reference. And then we also want to save our 3D curves of the model into one 3D sketch. And I'll show that in a while here. Let's bring up one of those models, and I think it is included in this one. Yeah. So if we roll to the top of the tree, here's my imported surface, and you can see I've actually made it a differentiated color to differentiate between my actual model and the reference model. Sometimes you can actually just delete a kind of ambiguous surface of it, and maybe it's this face right here. If it is a solid model, you can use delete face with the delete, not delete and patch, and now you have a surface body instead of a solid. This is important because you never want to accidentally merge it with your reference. Likewise, I have my curves that what I've done here is at the end of that last model, that conceptual model, I gathered up all these curves and into one 3D sketch, and then I disassociated it. That is, I deleted all the on-edge references of those curves and then rolled it to the top of the tree, because once you delete all those in-context references of your model, you can do that. You can put it anywhere in your tree. And so that's what I've done. So now what I have here is I have a surface and a curve reference for the curves that were remaining. So let's talk about that a bit. So in that last example where we have our conceptual model, the next phase, after you create your copy surface and copy curve references, I want you to start deleting all your surface features. So we're going to go in and look for our boundaries, and for our fills, you can do that with the feature tree filter. Let's do boundary. Let's just pick all of those. Let's delete them. And if you're not familiar with this advanced button in the confirm delete dialog, you should be, because this is really important. By default, if you've never used this feature, you have delete absorb features and delete child features turned on by default. If you do that, any of the features that you delete, their child references will be deleted also, as you can see as I expand that advanced button here. So normally, when you're working on these kind of models and you want to do what I'm going to do and delete the surface features without the curves, you want to turn off delete absorb features and turn off delete child features. And once you do that, and you pick your surface features, like I'm going to do right here, and hit my delete key, I'm going to delete all those, but it'll leave all the curves dangling. So if I turn off my filter, you'll see what happens. There it is. There's some dangling curves, and I'm just going to continue to do that. Now, I didn't gather up all of those, so let me just hand pick some of those and do the delete key again. Let's pick any remaining like fill features, and let's also get the surface utilities like knit and anything else I have in here like split, chamfer, delete face, delete all those. So what remains is, and we have this dome on top. Let's get rid of that. So what remains is this network of curves, but these are from the conceptual model, and they're not really connected to each other, kind of out in space. And they should be exactly what you see from the imported 3D sketch that I showed in the later model. So now that we've deleted all our surface features, the next step in all of this is to be able to build your curve network. Okay, so it's that time in this to start going through your tree and repairing those curves, those sketches, and make it a unified curve network. And so we can start to go through our tree, down our tree, and start to rebuild our curves. And it is an opportunity too to simplify our design, because now that we understand how we built it from the back end, we can take a look at it from the front end. And if I turn on the correct model here, so let's find it. Yeah, so here I've saved it so that I've taken those sketches, I've reordered them, I've built them into a curve network. So what you see remaining here is just a series of curves that define the design intent of my model. And I've changed my approach over the conceptual model, because now I have that reference right here that I can refer to, and I can actually more complete that curve network. You've also noticed that the feature tree here is been reduced in number of features, because as I go through this process, I've been able to simplify. And that's an important thing also. You want to simplify, make it as simple as possible, look at different ways to do things, look at ways to eliminate curves that you don't really need or references. Also planes, we can eliminate planes. You can see there's not that many planes in this model now that there were in the conceptual model. And so now we have a really good approach. We have a curve network that really well defines our model. And at this point, we have enough to really start doing our surface modeling. And so with this curve network, we want to start building our surfaces on top of this curve network. Now, let me just pause here and talk a little bit about splines, because there are a few 3D sketch splines in that curved network model. And I want you, if possible, to avoid 3D sketch splines. The reason I say this is because they are particularly susceptible to over-defining when design intent changes. An alternative to doing a 3D sketch spline, if you're not aware of it, is to use two 2D sketches to make a 3D projected curve. And if you're not aware of that feature, it's really valuable, and it's been in SolidWorks for quite a long time. If you go to Insert Curve, Projected, then what you can do is take and build two curves that are perpendicular to each other and their endpoints are attached. And with that, you can project those two 2D curves into a 3D sketch curve. For instance, if this curve along the edge here were to be defined, and if we roll back in our model to the right place, and let me go to a flat tree view, and I'll explain that in a little bit. It is in flat tree view. I think what you have to do is go all the way to the end, turn on and off tree view. Now I've got it here. So there's a curve right here. That's a 3D sketch curve. You could build that using a projected two projected 2D curves, and that'd be a good example for that. Also, if you do have to use a 3D sketch spline as like a bridge curve or something of that nature, try to avoid making it having any interim points in that sketch spline. What I mean by that is if you can build a 2-point spline, it's going to become more robust and actually become more robust when edits happen. If you do have to put in more than 2 points and you have interim points, consider going to a style spline, and especially a Bezier style spline, because they are more robust than the default SolidWorks spline. Yeah, so that's my recommendation for that. Also, how you constrain 2D and 3D sketch splines is important, and I'll talk about that in a minute here. So let's go to talking about this special constraint that I use that I find more robust than some of the other constraints. And if we go back to our model, I'll just demonstrate that. Let's go to this version 5 of the controller that has its surfaces, and let's talk about one of those. So if I take a look at one of these bridge curves that I created, and it's kind of hard to see here. There it is. So if we go here to this curve. So this is a curve I created after I created my fill to better define that way that fill flows from the handle to the elliptical area. And the way I constrain this, let me just delete the constraint and the curvature and pull it away and show you how I did this. So if you're not aware of this constraint, I don't blame you because it's rather hidden. So first of all, make your edge constraint with the edge of the surface and the spline. And then before you do anything else, kind of line up the magnitude of how you want it to come away from the actual surface. And then to invoke the face curvature or face tangency, you click on the spline, hold down your control key, click on the edge, and then also click on the adjacent surface. When you do that, you'll see over here in your property manager, you get two options. You get tangent face or equal curvature. And if you do one of those, you're going to have a constraint to that surface. And here's the beauty about it. It slides along the surface and maintains its constraint. The reason that's important and why I'm emphasizing this is if changes do occur to this surface, and rather dramatically, it has a better chance of surviving because of the freedom of this constraint to stay curvature or tangent to that surface, but yet kind of move. So I highly recommend that constraint. It's really valuable. Okay, so let me step through this model and we'll just kind of talk about it through PowerPoint and also through SolidWorks and showing it live. So if you look at any of my advanced models, you'll notice I use a lot of reference surfaces. Reference surfaces are valuable for creating other surfaces. They aren't part of the model, but they help guide your primary surfaces. They're especially important and required for fill surface because fill surface lacks a few options like boundary does to do normal to do draft, to do things like that. It wants to derive, the fill that is, wants to derive its shape from its surrounding boundary surfaces. And that's why it's important to create these reference surfaces, especially when you're using fill. So what I've done here is created two reference surfaces. And the way that I do this basically is I make them very simple. I create a couple 3D sketch splines in one 3D sketch that are just simple lines. They're all equal. They reference tangent to adjacent geometry, and I use that as a boundary surface for the first direction, those four, and then the other one that they touch as a second direction. And so I try to make it really simple, really robust. That's my reference surface. And that's to establish the tangency of how you want the fill feature to behave or end at that boundary. So with those, then I can go ahead and create my fill features. So here I've created my the rear of that elliptical forward area of the VR controller. And then when I've created that, I create the forward part of it, and then I create the dome. So with three fill features, I pretty much defined that front end of the controller. Now I can take a surface macro that is the chamfer feature, and I can create a chamfer between those surfaces. And it's just a quick way of getting that feature in. It doesn't necessarily follow my example of creating a curved network, but I know that that's a pretty robust feature, and then I can add it after I've created my curved network. At this point, I know that I have to trim away part of this forward area because I have to do my transition between this forward interface area of the controller and the handle. So I'm using a 2D sketch to trim away part of that surface that I created. And then I do a further trim to get these this remaining material to be at the chamfer to be perpendicular to that top elliptical face. So maybe we can go back to our model. Instead of me showing some of these features, we can just show it live. Let me go to this model that I had here. Let me escape that. And let's go back into the model where we create, and let me take it out of tree view. So if you're not familiar with what I'm talking about when I talk about tree view, there's two ways to look at your feature manager. You can look at your feature manager as you build features and as those features are absorbed by other features. That's the normal way of looking at it. If you want to look at it in a flat way, meaning you want to see how the features are actually created, and you can notice here in my flat view, here I have all of, if I roll up to this point right here, there's my curved network. Okay, even though these sketches are all absorbed into features further down the tree, in a flat tree view I can see them as I created them. And this is super valuable too when I want to go and edit that curved network to have this view of that. But for the example here, let's go ahead and let's roll forward. One thing you can't do in tree view is you can't create folders, just so you know that. In tree view, let's go and show regular view. Let's go back and highlight this feature in our model. Here we created this end, but you'll notice that what that's built on is a boundary surface. And that boundary surface is really pretty simple. It's basically two sketches. It's these 3D sketches that are just simple lines that are all equal to each other, and they're all constrained tangent to this existing curve network. And with that, now I can control the direction of the way my boundary surface flows. Okay, so first I do that top surface. You can see if I open it up, you get a really nice surface, and we'll talk a little bit later on about how fill works and why it's so successful. We'll save that for then. We do the bottom part of our cap, and then we start moving on to some more simple surfaces, which will be our boundaries for the top and bottom. So let's go back to our PowerPoint. Let me speak very briefly about fill. Okay, so if you're not familiar with fill, fill is a really special feature. I call it the crown jewel of SolidWorks. And it's the crown jewel because you can fill in between any number of surfaces and do it either tangent or contact. It's really optimized, or should be used in when you're doing advanced model, for anything that's 3-sided or 5 or more side. Anything that's 4-sided or 2-sided, use boundary. But for anything that's 3 or 5, use fill. The reason is because fill is a powerful feature that derives its own isoparam direction within the patch. And that's really important, as I showed earlier, why, well, I didn't show it earlier, it's later on in my presentation, how sometimes boundary even has this problem on 4 sides where you get degenerate edges or points in your surface. We'll talk about that hopefully in a bit. Anyway, there's also this option in fill called optimized. What optimized is there is 2 algorithms in fill, or the inside patch. One is called a Coons, and when you have a regular 4-sided surface, it kind of goes to that and uses that because it's very efficient. When it's 3-sided, you can still do a Coons patch, but what you'll get is something like what you see here on the left. What you have on the left, if you turn on your mesh, you can see you have it building a surface, but out towards these endpoints it becomes degenerate because the isoparams are all converging on the first and second edge of the fill. If you turn that off, now what happens is you get a different algorithm that solves for the isoparam direction independently of its surrounding tangent or curvature faces. And that's what makes fill so powerful. What makes fill the right solution for 3-sided or 5 or more side surfaces. Okay, enough about fill. Let's keep going. So here we're just building up our model with building the top of the handle, building the bottom of the handle, and then we introduce another macro surface feature, that is the chamfer along that edge to the same dimension as I earlier did on the interface area. And then we get to a point in our model where it gets a little more complex because now we have to jump that boundary. We have to make a smooth transition between our interface area and our handle area. So let's go back to the model and let's just show that in SolidWorks. If we roll back to one of these features in our tree, and now you can see we have 2 boundary features that are bridging the gap of those 2 chamfers between the handle and the interface area. Let's take a look at the second one. If we edit that boundary surface, what makes this work really well, and what works really well for boundary if you can do it, is just make it one directional. Once you make it one directional, then it has an easier time solving for the shape that you want. And in this case, you can notice I don't have any second direction curves. I just have two primary first direction curves, and I'm deriving the shape just off of those two curves. Furthermore, I've also weighted one of the boundaries here. If you look here at the first curve down here, it's its normal weight. But if you look at the second one up here, I've weighted it to be 1.5 instead of 1. And you can see as I continue to weight it, I'm changing my shape. But I'm changing in a very predictable way in what I want it to do. Now 2.5 is too much, so I'm just going to go back to 1.5. And that's pretty much what I want. That's how I want it to transition. So just know that's an excellent way to use boundary if you can just constrain it to just a single direction. So now at this point I have those references. I can continue on the bottom of the controller to fill out those areas. So I create another boundary feature, or let's say a boundary surface, and let me see if I'm finding it. Those are those. So yeah, so if we look at, I've created it earlier up the tree. Is this it? Yeah, probably. So I've created this additional, no, that's not it. That's the handle. You know, it's been absorbed into one of these other features. So let's go to the fill feature here. What's going on here? Okay, let's go back and find this. So maybe I did create just in this model, this version of the model, I created a boundary for this area. I didn't include this area over here because I wanted to control better the tangency by using this edge. So in some of the examples I'll give you after the presentation, I created two fill features here, but I decided to do as a boundary. Maybe this is after I refined it and found that this is a better solution. So basically what you see here is a boundary surface with some first and second directional curves, and you can see that with my mesh on, it flows pretty well. And then all I have left to do is to finish this one feature over here. I created that as a fill instead of a boundary, even though it's four-sided, because I find that fill does slightly better magnitude tangency than boundary does. The developer explained it to me one time that if boundary creates a tangent reference, it's at 1, and a fill creates a slightly better tangency. Also, you can see the isoparams are not matched with its surrounding surface, so it probably fills this area better, and I found after some optimization for that to be a better solution also. So, you know, interchangeably using fill and boundary to find the best solution is a good game plan. And then all you're left to do is to knit the thing together, but I have a few more things to do. I have this surface up here I have to fill. So let's roll forward. Let's talk about that a bit. So this surface right here, you're probably looking at it and say, well, why didn't I just create that as a boundary surface instead of a fill? Well, I'll tell you why. If we go ahead and try to make, let's just go ahead and try to make a boundary. So I'm going to use these edges as my first direction, and I'm going to use these edges as my second direction. And let's apply tangency here. You can see it's not very well defined. You know, it doesn't. I want it to be contact here, but it wanted to solve it to be near tangent. And the reason for that, by the way, is because these side curves here are coming in tangent to their first directional curves. That's not really the problem. I could probably put an interim curve in here and get this to look right, But the real problem is this. If we solve it and we turn on view curvature or display our curvature, you can see that we get some pretty nasty degenerate areas here in our surface. I can guarantee you this surface will not offset or shell. And this is the reason that you don't want to do this. And the reason why boundary doesn't work here is because its first directional curve at this point is tangent to the second directional curve. Boundary works best when the curves are near perpendicular to each other. That's when it works best. But if you get this kind of situation, it's not going to work. And you need to use fill. Because with fill, as I mentioned earlier, it does not derive its tangency from its surrounding surface patches. If we look at fill again, you can see, and we turn the mesh up, you can see that its isoparam direction in X and Y doesn't really relate to either of these four surfaces. It's deriving its own, but yet maintaining tangency. That's the power of fill, and that's why I call it the crown jewel, and super useful for doing advanced modeling. So the only thing left to do is to make it solid, and you notice I don't even have a knit here, because in the fill feature, if it is seeing it as a closed manifold surface body, you can actually click on make solid and merge and come out with your solid model. So there is our completed primary shape. We have lots more detailing to do to make it an actual product, but that's the hard part. So with that said, one of the other great benefits of doing this approach is that we've reduced the number of features in our model. We've decreased the rebuild time. And so, that's just a win-win. Also, we've made a model that's very editable. And just to put my money where my mouth is, let's go ahead and bring up a version of this. I think it's this V5 version. Let's roll it to the end. I'm not sure I have the right version here. Let me make sure I do. Yeah, let's go with, this is the completed version, by the way. I'll show that in a second. I believe it is this model, but I think what I first have to do is go back to my flat view. And now with my flat view, I'm seeing my curve network sketches up front in the tree. So I've highlighted a few changes here that I want to make. So here we have a sketch. It's very early in the model. I think this model is 65 features, big, and I have instant 3D on, so I don't even have to edit the sketch. I can just highlight the sketch, and I'm going to change this dimension here, which defines the depth of this part of the controller. Remember, this is early in the tree. Many features are referenced to this. I'm going to change this from 1.4 to 1 1/4 and rebuild. There, it doesn't look dramatic, but it is dramatic because there are all these other features that are built upon that primary curved network and surfaces. And it completely rebuilt the tree without error. Let's take a look at a few other examples of change. Here we have, let's edit this sketch. This is the forward profile of the handle. And I want to go in and make these conics a little more filled out. So I'm going to change the row value to 0.55 and get something that looks like that. Let's rebuild. And again, you can see that the tree's rebuilt without error, and it's changed that feature, of which many other features, especially these transitional features, have been built upon, but they've successfully updated. If we just do a Control Z a couple times, we can bring it back to where we were. There we are. Let's try one more. Let's talk about changing, let's change an actual 3D sketch. Let me pick something that I've highlighted here. I've got to find it. Let's see. Maybe I'll just find it by referencing it here. I know it's this guy. Let's go ahead and change this curve. So this is a 3D sketch curve, 2-point spline in our curve network. Let's turn off our plane so you can maybe see it a little bit better. So there we have it. So I want to change this to be a little smoother. Let's turn our curvature combs and let's do something like this. Okay. Tweak it a bit, play with it, get it to where I want it, and then let's rebuild. Again, model survives. And that's one of the bad boys that I talked about early in the presentation. You want to avoid, but if you do them right, they work pretty well. So I hope I proved to you that this is a valuable technique for building good, robust models. Now, I want to explain that it isn't completely bulletproof. There are features on this model that will break. I think this one I broke before when I changed this to like, let me see, I think I changed it, let's get my view correct here, to something like 8.5, and I changed this guy to 5/8. Oh, look at that, it survived. No, it didn't. Well, it survived, this fill feature survived, but it didn't give me the right result. And that's probably, this is better than it failing, right? Because now you can go in and you can edit some of these sketches. It's probably this interim curve here that needs to be moved. So let's just go and just move that because I've used that constraint that I talked about, the face constraint. Let's see how it's looking. Maybe this needs a little bit more lead in. Yeah, so you can see how that works. That is workable, and that's a joy because it's better than failing. I can just go in and kind of aesthetically change it to be what it needs to be. So, okay, so we're running out of time, and I want to give you your takeaways. So the takeaway is that if you divide your process up into a conceptual process versus a build it again phase, you're going to find that you can do all your experimentation up front, get that out of the way, not spend a lot of time noodling on things or making things perfect, but getting a strategy, getting something that you know it works. And then once you have that, build a curve network that defines your shape, builds it in, and make it as complete as possible of curves that define your design intent. Once you have that curve network, build all your surfaces on it. Now you're not going to be able to build all your surfaces on it. You're going to maybe have to introduce some more curves, but at least you've eliminated a big part of the problem, and that is that as the curve network updates, it's updating the surfaces robustly. And then the last step is to refine your model. Go back. It's not going to be perfect the first time around. You want to go back in and you want to test it. So you want to make some major changes, see what happens. If it breaks, find a different way to do something in your model. What you're going to find too is that it leads to simplification. And that's a great step too, to reduce the number of features in your model and make it easier to navigate, make it simpler for yourself and those that you pass your model onto.
Thanks for tuning in to today's episode. We hope what you've learned has been informative and can help you to better use some of SolidWorks advanced features. You'll see in the YouTube description a link to example models used in today's video. Feel free to download it, and you can explore these techniques at your own leisure. Also, we'd love to hear from you. so consider emailing me at the address you see here on the screen. If you need help on your design project or just want to know more about us, stop by our website at spannerpd.com or email us at hello@spannerpd.com. Take care, and I'll see you in the next episode.